moved.
Yep.
So the exam will be corrected sometime later today. We're going to probably wait till we get the 801 section done before we mount the grades, but I'll probably finish up correcting the exams from your crew sometime later today. So what we're going to do today is we're going to start a whole new section, and basically we're going to start a section that's brand new stuff. This is going to be the nervous system section, and we're going to start here with the idea of the nervous system as a machine. And the idea that I'm trying to get across in today's discussion is simply that we can understand the nervous system with respect to how it functions as a biological machine. There's nothing magical about it. It's just a biological machine. And that's the basic tenet we're going to approach it with. And we'll start with the idea of a three-box model. This is something that any of you who have done any computer science will recognize immediately. It's data in, analysis, and data out. We can think about the nervous system in the same fashion. We'll just have to modify it a little bit, and we're going to get into a black box pretty quickly that we don't understand entirely. But we are getting some understanding of it, and I want to begin to explain to you how we've gotten to those explanations of how the nervous system works. When we think about a biological system as opposed to a computer system, we think about, rather than data in, we think about sensory information coming in from the periphery. So as we're going through life, we're constantly monitoring the world around us. And we're monitoring the world around us with sensory information that comes into our brain. Now, I'm going to exaggerate this a little bit and talk about sensory input as being afferents. It's not quite right. If you take an anatomy course, you'll find that particularly with vision is part of the central nervous system, so it doesn't quite fit with this concept. But the idea still is we're taking information in from the periphery, we're taking it in through sensory systems, and we're then transporting that information into the brain. And so we'll begin here with sensory information in. That's to carry toward. These will be afferents. In fact, this term afferent comes out of the Latin, and it means to carry toward. Then we're going to take that information into the central nervous system. The central nervous system now will be the analytic unit. In the nervous system, we talk about this as being integration. So we're going to integrate the information coming in from the periphery. And then once we've integrated the information and made sense of the world around us through the integration unit of the brain and spinal cord, then what we're going to do is we're going to decide to do something. But to do something, we now have to invoke the peripheral nervous system, go back out to the periphery, and cause contraction of muscle, whether it's smooth muscle or cardiac muscle or skeletal muscle, or whether it's going to be glands. But we're going to effect, we're going to change something. Now this term efferent actually comes from the Latin. It means to carry away. So where we have sensory information carrying toward, we have efferents carrying away. Now the other way I remember the distinction here is that the meaning of efferent actually comes from the same word root as effect, to effect a change, to bring about. And so efferents are going to bring about a change, and the way we're going to bring about that change mostly is in causing movement or in glandular changes. So sensory in, analysis, motor out. Then I want to spend a little bit of time on sensory transduction, and we can't get too deeply into this. If you take a neurobiology course, you'll get down into the weeds of how all this happens. I just want to open up the idea here that in order to have sensory transduction, in order to understand the world around us, we first have to change energy in the world around us into the movement of ions across membranes. That's the idea of sensory transduction. And all of the information we're taking in, the way we make sense of the world, is through basically three kinds of sensory input. We take information in from the electromagnetic spectrum. For us, that's mostly vision. For other animals, it can be a little different. But for us, it's mostly vision. And then the other input that we can make sense of the world with is mechanical. The easiest way to think about that is touching something. You deform the tip of your finger, and in the process of deforming the tip of your finger, you start the movement of ions across membranes, which then goes through a cascade of events of electrical signals reaching your brain, and in your brain then you'll decide what that means. We have pretty good mechanisms for touching something and sorting out what it is, and that's all done through this mechanical response. The other mechanical response is audition, hearing. So as I'm standing here, I'm making noises, and those noises are nothing more than waves of sound that are moving to you. You're gathering those waves of sound, taking them into your outer ear and your middle ear and your inner ear, and then transferring it in your inner ear to a movement of ions across membranes. That's the first step in sensory transduction. Then those electrical signals are taken into the central nervous system, where in ways that remain somewhat mysterious, those electrical signals are now converted into understanding of sounds. Whether it's a bird you're hearing, whether it's a train whistle you're hearing, or whether it's language. We're taking that information initially by changing the movement of ions across membranes, but in the end, through all that movement of ions across membranes, we can make sense of the world around us. We can make sense of language. We can make sense of creating novel ideas from language. So all of that, much of that is basically mysterious. We have a pretty good handle on the sensory transduction, though. And then once we've come through the basic generalizations of how the nervous system works, we're then going to drill down and talk about the cellular organization of the nervous system. And this all begins with the discussion of something known as the neuron doctrine. The neuron doctrine holds that the fundamental structural and functional unit of the nervous system is the neuron. We accept that now. I mean, 130 years ago, that wasn't so widely accepted, and there was a tremendous amount of intellectual ferment to try to sort that out. And I want to tell you a little bit of the story of the founding of neurobiology in terms of these two major players. One guy named Santiago Ramon y Cajal, who was working in Spain, and Camillo Golgi, who was working in Italy. So they're two sort of antagonistic figures who laid out the idea of the cellular basis of the nervous system. And much of this was done through the insights of Golgi, who developed a new kind of biological stain, something known as the Golgi stain, which could stain neurons specifically, but only in small numbers, and we'll explain that in a little bit in detail. Then once we've laid out the ideas of the neuron, which Cajal and Golgi had argued about, and Cajal basically won the argument. Once we've settled that out, then we're going to talk about some of Santiago Ramon y Cajal's major ideas, which was the law of dynamic polarization. And to me, this is one of his major insights. Simply by looking at anatomy, by looking at sections through the brain, day in and day out for years, he came to a conclusion. Turns out he was right. This idea of dynamic polarization, which says that information moves in one direction in the nervous system. He described that as moving from the dendrite to the cell body to the axon terminal. He had only a vague idea of what kind of electrical signals were going to be involved here. That took another, 50 or 60 years to sort out. But these descriptions, the anatomic descriptions, which we still use, are really better described in a kind of functional description. Because once we understood the ion channels responsible for the signaling, we could then begin talking about a functional description of the neuron. And we now divide the neuron slightly differently. We talk about an input region, a conductor region, and an output region. And one of the hallmarks of these three different regions will be different kinds of ion channels. And we'll lay out the idea of different kinds of ion channels here today, but as we go through the discussion of the nervous system, we're going to spend a whole lot of time discussing the different kinds of ion channels, how they function, what kinds of ions they carry, and how they're similar and how they're different. But to start with, let's begin by simply saying that we can talk about the three-box model of the nervous system. In its basic tenet, it's the same as what you would see in a computer science course, and that is data in, analysis and data out. Now there's a lot between those, and if you're a computer scientist, you're just going to spend years going through those details. Similar though, in biology, we can imagine information coming in. This is going to be sensory information in. That sensory information now is going to be carried to an analytical unit, which will be the brain and spinal cord. Now in biology, rather than calling it analysis, we call it integration. What we're doing is we're taking information from all of the sensory input, which is being carried toward the brain and spinal cord, and integrating that information in the brain and spinal cord. When we talk about carrying sensory information in toward the brain and spinal cord, we talk about this as being the peripheral nervous system. And in this aspect of the peripheral nervous system, what we're talking about is sensory afferents. This is an important term in neurobiology. It describes how information is being carried. And when we think about sensory afferents, this comes out of the Latin. It means to carry. Toward. So to bring that into one package, what we're saying is that we are bringing sensory information in from the outside world. This sensory information then is being carried toward the analytic or integration unit, the brain and spinal cord, by sensory afferents. So this is going to be the peripheral nervous system. We're taking information from the periphery, from the outside world, carrying it toward the brain and spinal cord, and then in the brain and spinal cord, we're going to integrate that information. And the brain and spinal cord will integrate that information, and then we're going to make a decision, and then we'll go back into motor out. This too is the peripheral nervous system. And the motor out is carrying information on what to do. Away from the central nervous system or integrative unit to muscle or glands. So in its simplest form, we're taking in information, we're deciding what to do, and then we're doing something about it. The analogy I sometimes use talking about this, so we can think about one of our distant ancestors on the Serengeti plain, and the distant ancestor looks out and sees a lion. Well, that's sensory input. This person sees the lion. But in addition to the sensory input of seeing the lion, there may well be auditory input. This person may hear the lion growling or hear the lion breaking sticks as it's walking toward the person. If it's really close, then there may be sensory input in terms of chemical information like smell, if it's taste or really close. And so this is information coming in, but that doesn't do us any good unless we analyze that information and put it together into some sort of scenario. That is the lion walking toward us? Is the lion walking away from us? Does the lion look threatening? Has the lion just eaten? Does it look hungry? So we analyze that all that information. And then once we've analyzed that information, this brain and spinal cord makes a decision as to what to do. And that integrated information then goes out back into the peripheral nervous system. And in the peripheral nervous system, then we'll actually do something. So we'll send signals to muscle to say, run like hell. So this entire idea we do every day. As you're sitting here in the room, you're doing the same thing. You're taking in sensory information. Some of it's conscious, some of it's not. Your central analytical unit is deciding what to do with it, and then it sends that information out back to the periphery and does something about it. So those are the basic ideas of the nervous system. Now, it's pretty much a black box in here. We're getting pretty good at understanding how sensory information is transduced in the outside world, how it's propagated to the central nervous system, but actually how that sensory information gets to the central nervous system and then runs through thousands and thousands, perhaps millions of synapses to make a decision as to what to do. That's pretty much a black box. We have a pretty good idea of how signals go out to muscle. We have a pretty good idea of how those signals will activate muscle. But what's going on in the black box, that remains largely mysterious. We're working on it, but we still don't know. But what I want to impress upon you here is there's nothing magical about this black box, as far as we know. That as far as we know, we can base what's going on in this black box fundamentally on physical chemical principles. There's nothing metaphysical about it. It's just based upon the science of what we know about ions moving across membranes. That's a novel idea, and I want to tell a story here of where this came from, because it's kind of foundational for neurobiology. And the story is probably exaggerated. The story probably isn't quite as neat and tidy as it's commonly told. But the story is about a guy named Phineas Gage. And Phineas Gage was a worker in Vermont. And the story I'm going to tell you takes place in 1838. And what's going on in the 1830s, 1840s in the United States, and actually all over the world, is that the society is now beginning to be knit together by a brand new technology. A technology of taking steam engines, hooking those steam engines to wheels, steel wheels, and putting those steel wheels on steel rails. And this is a brand new form of transport. Now we're no longer tied to moving things in canals. We can now move things on rails. We can move people on rails. Where up to that point it had been a 3-mile-an-hour world, now we're starting to increase rates of movement by an order of magnitude. Just an incredible transformation in the society. But part of that transformation required laying out all of the railroad beds. And one of the 19th century insights, and perhaps in the 18th century, was to learn how to do surveying. And in the 19th century, what they could begin to do is they could survey a line where they wanted to put the railroad. And then they could come along and lay down that railroad. But the problem is when you put a several tens of ton locomotive on steel wheels, on steel rails, you're not going up a very steep grade. So that meant that all of those roadbeds had to be graded to no more than about a few percent grade. So that meant there was a tremendous amount of activity in grading and moving dirt, blowing up rocks so that they could put in these railroad beds. And that was Phineas Gage's job. Phineas Gage was a foreman on a gang that would go out and drill holes in the rock. And then his job was to blow up the rock with black powder. And the story is that in the morning they would go out and they would drill holes in the rock, sometimes several feet deep. Now remember, Phineas Gage is working in Vermont, and if you've ever been to Vermont, you know it's very hilly. So there's a lot of hills that have to be taken down to grade. And it's really rocky, so a lot of rocks to be blown up. And so what they would do is they would go out and they'd drill holes in these granite rocks. And they'd make them a couple feet deep maybe. And then they would put a fuse in. Then they would put black powder into that hole. Dynamite wasn't invented until 50 or 60 years later. And dynamite was actually a safety invention. At this point, they have to use black powder. Black powder is pretty unstable. So they put black powder, gunpowder, down into the hole. They laid the fuse in. And then on top of that black powder, what they had to do was take clay or sand. They'd pour clay or sand into that hole on top of the black powder. Then they would come along with a tamping rod, and they go, dum, 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 and they would tamp that sand down onto the black powder. And then when the black powder was ignited, the force of the explosion would go down into the rock and break the rock. It looks like what Phineas Gage did this day is that he put the black powder into the hole, he laid the fuse, but he'd forgotten to put in the sand. So he took this steel rod, it was about 3.5 feet, 4.5 feet long, it's about 1.25 inches in diameter, and he started to tamp the sand, but there was no sand in there. And instead, he struck a spark. When he struck a spark, it ignited the black powder and drove the rod up through his cheek and out the top of his head. Now, if he died there, which is the most likely event, we never would have heard about it. But Phineas Gage survived, and there's a whole story about this guy surviving. First, he went down like a shot, was unconscious. Someone went to pick up the rod. It was covered with grease, which was basically Phineas Gage's brain. And about this time, Phineas Gage sits up. Okay. And so they put him on a cart. They haul him 3/4 of a mile in a horse-drawn cart back to an inn. He sits on the porch. The doctor's called. The doctor arrives, and Phineas looks at him and says, "I've made a job for you today, Doc." And the doctor starts to tend him, and Phineas coughs, and about a teacups full of brain goes spurting out the top of his head. And to figure out where the damage was, the doctor, remember this is well before germ theory, the doctor takes his finger and sticks it down into Phineas Gage's brain, feels around, pulls out some of the extra bone, and was a pretty good anatomist. He had a pretty good idea where the trajectory of that rod had been. It had gone up through his forebrain. Now, if you read the original documents, it's just astonishing. About 10 days into Phineas's recovery, mold starts to grow out of the top of his head. Doctor comes in, cleans it out, gives him a bandage. There's an enormous abscess on his forehead. He drains the abscess. For the rest of his life, Phineas has this great scar across his face because of the draining the abscess. But he survives. He manages to survive. Now, initially, Phineas is not the guy he was before. He's difficult. He's not the same person. He's changed his personality. And much of the story about Phineas Gage revolves around the idea that he was no longer the person he used to be. He used to be this convivial guy, family man, so on and so forth. He's no longer that person. We think that's probably not quite true. We think he probably did recover over the years. But still, the idea was the man's had brain damage and he changed who he was. So maybe there's some indication that there's a connection between what our brains are and who we are. It's the first indication of that. Well, he does recover somewhat. He goes and he's having a hard time holding a job, and I'll show you an image of him in a minute. He has a hard time holding a job, so he moves from New England and he goes to, of all places, Chile. In Chile, he is a stagecoach driver. So he must have been doing something all right. He was running a stagecoach line. But then he started to get sicker and sicker. He started to have seizure events. And it's not surprising. We know now that when you do damage to the brain, you often end up as seizure events as a sequelae or sequelum to the brain damage. In fact, the numbers are pretty worrying. If you have head trauma with internal bleeding and a fractured skull, 40% of those individuals will be epileptic inside of 3 years. So it's not surprising having a rod, a 1/4-inch rod, an 1.25-inch rod go through his brain, that Phineas Gage became epileptic. And he got sicker and sicker. He died in 1860. But by that time, he was in contact with his family. His family had moved from the farm in New Hampshire and moved out to San Francisco and settled in San Francisco. So he set sail from Chile, went to San Francisco, settled in with his family. But he died in 1860 of seizure disorders. At that point, information got back east. It got back east to the doctor. And they told the doctor that Phineas was dead. And the doctor said, "I want the head." And so they disinterred Phineas, and they sent his head back to the doctor. And to this day, the head, Phineas Gage's skull, is in a museum in Boston. And we still have these pictures. So this first picture is one that turned up, oh, I guess it's about 12 years ago now. And the picture on the left is a picture of Phineas Gage. And when it was initially discovered, it was discovered in New Bedford, Massachusetts. And New Bedford was an old whaling town. And so when this picture went out onto the web about 2009, 2010, it was labeled whaler with a harpoon because it came from New Bedford. But of course, there are any number of whaling aficionados out there. And so they looked at this picture and they said, that's no harpoon. And they also said, who ever heard of a one-eyed harpoonist anyway? And when they began to look more carefully, when they blew up the image, they could see that on the rod there was an inscription. And they could read the inscription. And the inscription was the story of Phineas Gage's accident. And what was going on here is Phineas Gage, because he couldn't be employed as his old job, was going around to different towns as a kind of freak show, showing what had happened to him and carrying this rod with him wherever he went. And you notice he's lost his left eye. He's blind in that eye. What had happened is the rod, the pointed end of the rod, had gone up through the left side of his cheek and out the top of his head. And this is his skull. This is actually the picture of Phineas Gage's skull, where you can see the orbit of the left eye is all broken. Here's the partially healed breach in his skull, and this region here is enlarged. So the rod has gone up through the left side, through the back of his eye, and out the top of his head. So again, the major idea here is this is one of the first indications that people began to say, well, maybe who we are is not our soul. Maybe who we are is our brain. It's a philosophical sea change. We now think that maybe we can understand how the brain works, and from there understand who we are as human beings. And basically since 1860, we've been on that quest, trying to figure out how the brain determines who we are. And I was trained as a neurobiologist. I find this question of how does the brain work a fascinating series of questions. And to me, it's a fundamentally human thing to do. There's no other creature on the planet that can ask the question of how do I feel the way I feel? How am I the way I am? And begin to explore what that means physically and chemically and physiologically. We can do that. We're humans. To me, it's philosophically equivalent to something like the Hubble telescope, where you send this telescope up to orbit Earth and it looks back at stars that were created within a few hundred million years of the beginning of the universe. We're looking back into deep time. No other creature can do that. It's all based upon our philosophical outlook of the world. It's based upon our scientific ability to do those things. Now, having said that, sometimes I wake up and wonder, what have we done? Because an understanding of neurobiology, for sure, as we move through a better understanding, is going to lead us to greater and greater understanding of long-term diseases in the brain, degenerative diseases in the brain, and will allow us to perhaps fix these problems, which come on particularly with age. But there's also a downside of it. The more we understand of how the brain is related to who we are, the better we can affect the brain and what it does. We will be able, probably in your lifetime, to decide what kind of children we want. What kind of channels do we want in these children? What kind of receptors do we want in these children, so that we can make them smarter or more musical or more athletic? And you'll be able to make that choice. I think it's a terrible choice, but the science will be there to do it. Even now, there are aspects of pharmacology that can alter people's behavior. And we all know this. You've all been through this. It comes to finals time, and you haven't allocated your time as well as you should have. There's a deadline. The exam has to be taken in 3 days. Studying has to be done. There's no time for sleep. How am I going to get this done? But you know, someplace out there, somebody has some Adderall and a couple of Addies. You're good for a few days. You'll be able to focus. You'll be able to learn that material. You'll be able to stay awake. But then there's the ethical question, just on this simple idea. Is it ethical to use performance-enhancing drugs to enhance your academic performance? We've decided in athletics it's not. I mean, there's a whole brouhaha about using various performance-enhancing drugs in athletic competitions. Well, should we be able to do it in academic competitions? Should we be able to find drugs that affect a particular glutamate transmitter in the brain and help us learn better? Should we be able to do that? I don't have an answer to it. I do know that if I'm in surgery, and I know the surgeon's been up for 20 hours, I hope that surgeon has something on board to keep him alert. So how do we parse all this out? How do we decide what's ethical and what's not ethical? And these are decisions in a democracy you as citizens are going to have to figure out. It's coming down the line. And in the next 50 years, these are decisions that will have to be made. Now, maybe it'll all be overtaken by AI and nothing will matter, but I tend to think biology is still going to have some important influence on our lives, and we're going to have to make ethical decisions about how we use that biology, use that knowledge to affect brain function, affect our personalities, affect how we regulate society, and how we can control members of the society. What are the rules for that? Because we're going to figure out how to do it. We'll see how it all turns out, or at least you will. But all of that is to say that the nervous system is this really interesting topic. But just understanding how the nervous system functions has a certain level of fraught possibilities that I think we all have to think about as we begin to see how we unravel the function of the nervous system, and we'll certainly unravel it. Well, let's move on from that soapbox and begin thinking a little bit about the simple idea of sensory transduction. Everything we know about the world around us comes from three sources of energy. The first one is going to be electromagnetic. For us, this is going to be light. The second one is mechanical. I think the easiest one to think about in mechanical is touch. But in addition to mechanical, there's one that's a little more sophisticated, and this is hearing or audition. The third form of energy that we use to take in the world around us, and almost certainly is the oldest of the lot, is going to be olfaction. Just a fancy word for smell, and taste. These two, taste and smell, are under the rubric of chemical transduction. What all of these have in common, whether we're talking about electromagnetic or mechanical or olfaction, what all of these have in common is that it's an energy form that is transduced, say changed, to ion movements. Across membranes. There'll be a whole host of these. We're going to go through some of the major ideas of how ions move across membranes, how they generate electrical signals. If you take more neurobiology courses, you'll see more and more detail. If you take a neurobiology course, a cellular neurobiology course, you'll go through how all of these different forms of energy are transduced to movements of ions across membranes and get into, at least to some degree, how that information is carried into the analytic unit and into the site where we're going to integrate the information, the brain and spinal cord, and how rudimentarily, how some of the information is processed. But for now, I just want you to hold on to the idea that we're going to move ions across membranes. But I also want to point out a couple of other things here, that different creatures have exaggerated these different means of transduction in different ways. Now, for us, electromagnetic is light, but it's limited. We can only see between about 380 nanometers to about 750 nanometers. 750 nanometers is red, 380 nanometers is violet. Now, if we move beyond 750, we get into something called infrared. This is heat. If we move in this direction below the 380 line, we now get into ultraviolet. And that ultraviolet light, for us, is not visible. If you ever get a chance, it's worth taking a camera that has a CCD card in it that's sensitive to ultraviolet light, shorter than this 380 nanometers, and go out and start taking pictures of flowers. Because if you do that, you'll find that there are patterns in these flowers that you never realized existed that are reflecting ultraviolet light. And those flowers are not beautiful because you like to see beautiful things, although we have bred a lot of flowers, but the flowers are there to attract pollinating insects, and the patterns of color in those flowers are to attract pollinating insects. So if you begin looking at things like honeybees, honeybees can see light down 350, 340, maybe as low as 330 nanometers. They can see that short wavelength light, and they can now pick up patterns in flowers that are generated by that short wavelength light. We can't see it. If you go in the other direction, up into the infrared, we can't see with our eye above about 750 nanometers. Now, we've generated night goggle vision. We can do some fancy tricks and see into the infrared. But there are animals who figured this out long ago. If you look at, in this area, it's be a rattlesnake, but all North American poisonous snakes, except the coral snake, are pit vipers, whether it's the water moccasin or the copperhead or the rattlesnake. And what characterizes a pit viper is that between its nostril and its nose and its eye, there's this clear pit. That pit has an aggregation of nerve endings. Turns out evolutionarily, those nerve endings have been aggregated from all over the face of the animal, and they're heat sensors. So the normal heat-sensing neurons are now aggregated in this one spot in the pit. What that allows these pit vipers to do is it allows them to go out at night and hunt, because they're hunting warm-blooded creatures. They're hunting things like birds and small mammals. And the birds and small mammals are unaware of the snake, but the snake is aware of them because the snake can image those creatures using the pit and the infrared heat, the heat signature, the infrared given off by those warm-blooded animals. Can sneak up on those animals and have dinner. All of that is because they can actually image on their somatosensory cortex. They can actually image the heat signature from these animals. There are other animals that I find even more remarkable. There are sharks and rays. Sharks and rays can sense electromagnetic fields in the water. All creatures, because of the way they're separating ions across membranes and having currents generated with the movement of ions across those membranes, all creatures generate an electromagnetic field. As you're sitting there, you're generating an electromagnetic field. Now, we have not evolved mechanisms to recognize that field because we live in an insulating environment of air. We just can't sense it very far away. But if you live in a water environment, particularly a saltwater environment, then these electromagnetic fields will propagate some distance. And so you've probably seen these images where there's this fantastically beautiful ray, and he's gracefully swimming along the surface of the sand, and suddenly there's a kerfuffle, and the animal has dinner. What that ray can do is it has, again, between its eye and its nose, it has an indentation. It's given another name. It's called the lamprey of Lorenzini. And again, there are sensory neurons that are aggregated at that site. And those sensory neurons can sense electromagnetic fields. Those sensory neurons are so sensitive that they can sense a flashlight battery over something like several kilometers, because they're looking at microvolts per millimeter. So when you scale that up, they're really, really sensitive. So they can recognize the electromagnetic signature of animals in the aqueous environment around them. Some animals some fish in the Amazon, where it's really, really muddy and they can't see anything, they'll in fact communicate through these electromagnetic fields. There are electric fish that do that. But again, this is something we have no consciousness of. We can't imagine that at all. And the final one I want to tell you about with electromagnetic is that some creatures can sense the electromagnetic field of the Earth. They basically have a built-in compass. We haven't had compasses until about the last 1,000 years. But there is an electromagnetic field of the Earth. And that's why we can take a compass and have it point north, more or less. And there are some animals, and it's not clear how. It was thought for a long time there was a piece of iron embedded in tissue between the eye of the bird and its beak. It's not so clear that's true anymore, but they have the capacity to sense the electromagnetic field of the Earth. And in so doing, they have a built-in compass. And so you can take something like a homing pigeon. You could take a homing pigeon out 500 miles from its home loft, throw it up in the air, and it will come home the same day. Take it out in any direction, it will come home the same day. In part, it's doing a number of other navigation tricks, but in part, it's sensing the electromagnetic field of the Earth and using the electromagnetic field of the Earth as a signal to find its way home. To me, I find this astonishing. I can't find the garage without a GPS. And yet these animals are capable of doing this all on their own. Then mechanical. Mechanical is one that we're all aware of. We take it for granted, but we're all aware of it. If you reach out and touch something, you know it's there. And we've all had the experience that we have forgotten that we left our keys in our backpack. And it's late at night. And we come home and we realize, oh, keys are in my backpack. So you have to open up your backpack, fish through your backpack in the dark, find your keys, and just with your fingers, find your keys in your backpack, and then sort your keys and start figuring out which key is to your bicycle, which key is to your car, which key is to work, which key goes to the house. Sort it out, find the lock on the door just by feel, put the key in the lock, open the lock, and walk in your house. All of that by touch. That's all mechanical. That's all done because what you're doing is you're touching something and you're changing the shape, the form of the tip of your finger. You're running your finger along that structure, and from that you're using the somatosensory cortex and a whole series of integration sites in the brain to say, those are the keys. Ah, that's the house key. That's not the car key. Sorting it out and using that information to get in, all through touch. To me, the even more astonishing sense of your transduction is hearing. And I won't go into a lot of detail with this, but I will say that in your inner ear, you have these cells. And the cells are called hair cells. It's a terrible misnomer, but basically these hair cells have cilia on them. These are the cilia. And the cilia are mechanically connected to a channel. Now, as I'm speaking here, what I'm doing is I'm setting up sound waves, and I'm sending out sound waves. And sound waves are nothing more than compression of air molecules, followed by a region of less compressed air molecules. And what you're doing is you're picking up those compressions. Those compressions are bouncing against your tympanic membrane, vibrating the tympanic membrane. It's your eardrum. Those signals on the tympanic membrane are being amplified by some tiny bones called the ossicles. And those ossicles now are moving a window in the cochlea. And when they move the window in the cochlea, they're setting up waves in that cochlea. It's an enclosed space. And these hair cells sit on a membrane, so that when that movement comes through that fluid, it moves these cells. You get some advantage of the movement, but in fact, what will happen is these movements can be so slight that because of the mechanical advantage of the cilia and the channel, that you can move just a few angstroms, open the channel, and allow ions to come in. And that's the beginning of sensory transduction. These tiny movements are setting up electrical signals that are being carried to your brain. And in your brain, those electrical signals are being interpreted as perhaps language. We're pretty good at that. I mean, we have an astonishing ability to hear sound and repeat it. I mean, some people have perfect pitch. And if you ask someone to sing a particular note, they can take that sensory information in, decide what motor neurons to activate just the right motor neurons going to their larynx, and make a particular sound. That's as foreign to me as navigating by the electromagnetic fields of the earth. But some people are able to do that. And all of that begins with this movement here, the sensory transduction, and then a whole bunch of magical things that go on in your brain. I mean, it's quite magical. What's going on right now is the fact that I'm just making these sounds. You're taking those sounds in, you're interpreting those sounds, and from that you make language. And from that language, you can understand what I'm saying. And from your understanding of what I'm saying, you can then put together whole new ideas. You can then take that information and put it together in different ways, remodel it, and come up with your own ideas, your own concepts. All that's done inside the black box of the integrative unit. We don't really understand how that happens. We'll get there, but we really don't understand yet how that happens. Then olfaction, smell, the oldest of all of the sensory input systems. We think it's the oldest because when our distant ancestors, probably during the Cambrian explosion 500 million years ago, maybe beyond that, in order to find something to eat, they basically had to sense something decaying. And they would sense something decaying, and they would sense the amino acids and other molecules in the water column and follow that gradient till they found something to eat. And that was the beginning of olfaction or smell. To this day, we can to some extent, but you can take animals and get them to follow a gradient. Take a bloodhound, and it's effectively going to follow a gradient of these these molecules that are binding to receptors in their olfactory system and setting off a series of signals in the olfactory system then to make sense of the world through olfaction. Similarly, there's taste. We're all familiar with this. We all eat. And so we can taste things. But interestingly enough, there are only a handful of tastes. What you can actually taste is sweet, salt, bitter, sour, and something called umami. Umami is the most recent discovery of those. It's basically what you're tasting is the amino acid glutamate, but it takes a little sodium along with it. But we know that when we eat something, we have many, many, many more flavors than just those 5. And the reason we can have more flavor than just those 5 of taste is because we're mixing and matching olfaction with taste. We're mixing and matching what we smell with what we taste. And there's an interesting trick you can do. It's really worth doing. Class is small, I could probably even do it. If you go out and buy a bag of jelly beans and then stick your hand in the bag of jelly beans, don't look at the jelly bean because that'll give you a hint. Hold your nose and put that jelly bean into your mouth and start chewing it. That jelly bean will be sweet. But until you open up your nose and get the aromatic molecules from that jelly bean up into your olfactory system, you can't tell what flavor it is. It's sweet, But not until you invoke the olfaction can you say it's one of those dreadful flavors like cinnamon or lemon or what other artificial ingredients they put into those jelly beans. But that's a combination. And some people are remarkable at this. I mean, there's sommeliers who can taste a wine, taste two wines, grown in vineyards no more than a fraction of a kilometer apart, and say where the vineyard was, because they can taste the difference. That's not just taste. That's a combination of taste and the aromatic molecules, the volatile molecules that are coming out of the wine that they're recognizing in their olfactory system. It's a combination of that. But again, regardless of how we're interpreting the world around us, the beginning of that interpretation comes through sensory transduction. And the sensory transduction comes from these three basic forms of energy. It's either energy stored in chemical bonds and shapes of molecules, or it's mechanical movement, or it's electromagnetic. That's all the information we're taking in. And all of our consciousness of the world around us comes from these, and they're all somewhat limited. How late are we? Well, let's take a break. And we'll come back and talk about the neuron doctrine, if there are no questions. We can start again. Where we're going to begin here is with a kind of definitional thing. It's called the neuron doctrine. The neuron doctrine is accepted pretty much as gospel now in all of neurobiology. It's the foundational concept upon which all modern neurobiology is built. And the neuron doctrine says, basically, that the neuron is the fundamental, structural, and functional unit of the nervous system. This is an idea that grew up in the late part of the 19th century and the early part of the 20th century. And up to that point, in the late 19th, early 20th century, there was a big argument going on in neurobiology. And there were two theories. One group were said to be the cellularists, and the other were said to be the reticularists. The cellularists held that the nervous system is constructed from individual units called neurons. The cellularists said we have these individual separate structures. We don't know how they talk to each other, we don't know how they communicate, we just know they're separate structures. The reticularists said that's nonsense. They said that all neurons are connected to one another by cytoplasmic bridges. What they're basically saying is that the nervous system is said to be a syncytium. Everything is connected to everything else. Every neuron is connected to everybody. All other neurons. It's just basically this one giant gamish of interconnected cytoplasmic bridges of neurons. That it's one giant cell, effectively. And there were two major proponents of these two ideas. There were several, but one of the major proponents of the reticularists was a guy named Camillo Golgi. Camillo Golgi was an outstanding morphologist. He was an outstanding microscopist. Camillo Golgi is the guy for whom we name the Golgi apparatus, because before we had electron microscopy, 70 years before we had electron microscopy, Golgi thought he saw something inside cells. Nobody else believed him, but he thought he saw something inside cells that was this sort of structure. And that was the Golgi apparatus, and so we named that for him. So he was an outstanding microscopist, an excellent pathologist. And he was working in Pavia, Italy. At this point, Italy, Germany, England are at the heart of scientific discovery. And so he's working in the midst of scientific ferment in northern Italy. And he's working on trying to understand how the nervous system is organized. And he invents something which is named after him, called the Golgi stain. Up to this point, up to the invention of the Golgi stain, almost all of the dyes that were used to look at neurons were aniline dyes. They'd been developed by the coal industry in Germany, and there were a whole series of chemical dyes that allowed the histologist to look at things like epithelia or connective tissue. But when they applied those dyes to the central nervous system, what they would see is literally thousands and thousands of cell bodies, nuclei, in every section, because the neurons are packed about as tightly as you can get them into the central nervous system. So when they used the standard sort of histochemical dyes, it was just confusion. They saw too much. But the Golgi stain wasn't based on the aniline dyes. Don't remember this, but it was based on something called chromium and silver, Ag. Salts. Basically, the chromium and silver made a black precipitate inside the cell. We know now that it was attaching probably to the intermediate filaments, the neurofilaments. It wasn't known at the time, but what they did recognize is that with the Golgi stain, you would get these black precipitates that stained or labeled neurons entirely. In other words, it stained the whole structure. It didn't just stain the cell body or the nucleus, it stained the whole structure. Well, that was an advantage. But oddly enough, this staining only worked on about 1 to 2% of neurons, of cells. Well, initially you would think a label that only marked 1 in 50 or 1 in 100 of the cells wouldn't be of any use to you. But what it did is it reduced the background noise, where before with the aniline dyes, they could see all of these cells. They couldn't make any sense of it at all. But now they would see a full cell, and they would see it only in about 1 to 2% of the cells. So that allowed them to see individual cells. Now, amazingly enough, for reasons I can't to this day understand, Camillo Golgi took that data and said, all these cells are interconnected. Now, to be fair, at that time, the resolution of the light microscope simply wasn't sufficient to be able to recognize the narrow gaps we now call synapses between neurons. Just couldn't see them. And because they couldn't see them, they assumed the cells must have fused with one another. Well, and so to be fair, you can see where the reticulus got their idea. But at the same time, in the late 19th century, 1880s, 1890s, there was a fellow named Santiago Ramon y Cajal. Cajal had kind of an interesting history. Cajal's father was a physician, but Cajal wanted to be an artist. He really wanted to be an artist. But his father said, son, go do something useful, and don't just be an artist. So Cajal went to medical school. And he always retained this interest in art, though. And what Cajal did is he became an histologist. In addition to teaching anatomy, particularly Valencia, the University of Valencia, then later at Madrid, he began to look at the cellular composition of organisms, and particularly the nervous system. And in so doing, he employed the Golgi stain. And he would generate preparations of brain from any number of different kinds of animals, and he would stain them with a Golgi stain, and he would then go to the lab in the morning, and he would sit down and look at those slides. He would just stare through the microscope, looking at slide after slide after slide after slide. And then in the afternoon, he would go out and take the afternoon off. He'd go out to the park and feed the pigeons, kind of hang out. And then in the evening, he would come back to the lab, and without looking at what he looked at in the morning, he would draw from memory what he had seen. So he was using his brain as a kind of an averaging device. Because if you look at even the Golgi stained neurons, they all look a little bit different from one another. And what he did is he brought together what he was seeing so he could categorize all these different shapes of neurons and say, that's a particular kind of neuron. And from that, from looking at cell after cell after cell for years, he came to the conclusion that each neuron is a separate cell. He even named parts of the cell, and I'll give you this and we'll go into a little more detail. He said there was one region which he called the dendrite. He said there was another region called the cell body. And what characterized the cell body is that he could see a nucleus. He'd always see the nucleus in the cell body, always confined to the neuronal cell body with the nucleus. Then there was this great long extension he called an axon. And then he called this thing the axon terminal. Now, one of Cahal's major insights of all this, and again, I find this remarkable because he just did it entirely from the anatomy, looking at cell after cell after cell. He said he generated something called the law of dynamic polarization. He didn't really understand, except very, very vaguely, that there's something electrically going on inside these cells. But from his anatomical observations, he came to the conclusion that there's unidirectional flow of information in neurons. The law of dynamic polarization is just a fancy way of saying information is polarized, it's moving only in one direction. And he said the information flow goes from the dendrite to the cell body to the axon terminal. So Cahal's contributions here are first to say that the nervous system is made of individual units called neurons. And then to say that the information in those individual units is flowing in one direction, from the dendrite to the cell body to the axon to the next cell. He didn't know how that was going to happen. That came later. But he knew that there was going to be unidirectional information flow. Those are his major contributions. And I think you can see from that law of dynamic polarization, the unidirectional flow of information, if all cells are connected to every other cell, if everybody's interconnected by cytoplasmic bridges, it's really difficult to see how you get information flow in one direction or another. It's just going to disperse throughout this gigantic syncytium. So it was a really important insight to say we can get unidirectional information flow. And around, I think it was 1898 or so, Cahal left his lab in Spain and started on a circuit. He basically went to Italy, and he went to Germany, went to England, and he was on the road. And he was giving these talks, talking about the neuron doctrine. And it was from those talks that the rest of scientific society, the academic community, recognized this idea of the neuron doctrine. After his tour, pretty much the neuron doctrine had taken hold. People recognized it as true, except for Golgi. Golgi held on to this ridiculous idea. And more or less the end of the story is in 1906. In 1906, Santiago Ramon y Cajal and Camillo Golgi share the Nobel Prize. And they share their Nobel Prize for Golgi developing the stain and for Cajal using the stain to describe the nervous system. But Golgi used the opportunity in his seminar, because every time you have these presentations, the Nobel Prize winner gives a seminar, a talk about the research. And Golgi got up and started talking about his research, and he went off on this tangent about how he was right, and Cajal had completely screwed it up, and Cajal was completely wrong, and Cajal was an idiot. Cajal got up and gave a very dignified diplomatic talk and thanked Golgi for developing the stain and thanked Golgi for all of his contributions, and then he gave his story about the neuron doctrine. After that, they hardly ever spoke. They hated each other to the end of their days. And it was all because Golgi couldn't accept what Cajal had found. And in fact, if you look at the way neurobiology was taught in the Italian medical schools, all the way into the 1930s, they followed this reticulus idea. It was wrong. The rest of Europe knew, the rest of the world knew it was wrong, but because of Golgi's influence on academics and also probably politics in the 1920s and 30s in Italy, they held on to the wrong idea of the reticulus idea, the syncytial idea. And so it's just a story here of how political frameworks can affect what beliefs are in science, regardless of what the truth is. But having said that, these two guys made enormous contributions. Golgi contributed the staining, the technique, and Cajal interpreted that information from the stain, which revolutionized all of neurobiology and said neurons are the individual units. And from there, people then had to begin thinking about how these cells were going to talk to each other. And we're going to spend a lot of time thinking about how these cells are going to communicate. But what we've done so far is we have described the so-called anatomic description. I describe this as the anatomic description of the neuron. And to this day, we use those terms. But I think there's a better way. It's more descriptive, and we'll see as we move our way through this why it's more descriptive. And that is a functional model. This is a functional description of the neuron. And I'll pretty much draw the same thing. It's one of my pineapple neurons. Neurons don't really look like this, but diagrammatically we can use it. And you'll notice that it's pretty much the same shape that I drew on the upper board, where Cajal described this as dendrite, cell body, axon, and axon terminal. We can change that nomenclature just a little bit. And we can change that nomenclature now to include the functional parts of the neuron. And we can group together this dendrite and cell body, and we're going to call this the input region. And when we say it's the input region, what we mean is that the input region receives information from nearby neurons. You can think of the input region as the receiving region. Now, I'll mention it here, and this term will make more sense to you later, but I want you to hold on to the idea that when we talk about the input region and the receiving region, this reception of information is carried out by something known as ligand-gated ionotropic channels. Broadly speaking, these ligand-gated ionotropic channels can be said to be neurotransmitter. Operated receptors / channels. We'll see later that the protein, which is the channel, and the protein, which is the receptor, is all one. But if you hold on to the idea that this input region is distinct from the rest of the cell because it's characterized by this receiving area known as the input region, and that the input region is enriched for these neurotransmitter-operated receptors or channels. Hold on to that. That's going to be important. Then this region, which Cajal had termed the axon, is now called the conductile region. We're going to see as we work our way through the details of the story that the conductile region propagates action potentials. And the reason that it propagates action potentials is that this portion of the neuron is enriched for a kind of channel called a voltage-gated channel. Another term for the voltage-gated channel is a charge-sensitive / operated channel, where the input region is characterized by transmembrane proteins that will bind to neurotransmitter and open channels. Those kinds of receptors are largely devoid from the membrane in the axonal or conductal region. Instead, in the conductal region, we put a different kind of transmembrane protein, a different kind of channel, a channel which is operated by a change in charge, which we'll call voltage. And these channels are particularly, we'll see, voltage-gated sodium and voltage-gated potassium channels. And then out here, this region now gets a new name. Rather than calling it the axon terminal, it's now called the output region. If we look carefully at the output region and we look at it in an electron microscope, we see that one of the things that characterizes the output region is it's just full of synaptic vesicles. And these vesicles are filled with neurotransmitter. It's called the output region because one of the things we're going to see is that these vesicles are going to fuse with the membrane by exocytosis and release neurotransmitter. Where the other end of the cell is the input region, this is the receiving end. This is receiving neurotransmitter from neighboring cells. The opposite end of the neuron is the output region, and it's spewing out neurotransmitter. Now, it's going to be, this neuron will be precious close to its neighbor so that this neurotransmitter can bind to the input region of the next neuron. But fundamentally, when we look at just the neuron, we have an input region, which is receiving information, and an output region, which is sending information in the form of neurotransmitter. The other characteristic that separates the output region here is voltage-gated calcium channels. And particularly voltage-gated calcium channels responsible for neurotransmitter, abbreviated NT, release. Now we're going to get down into the weeds of all of that. We're going to describe how all of that happens and how information flows from one end of the neuron to the next. But for now, just recognize that we have these two naming systems. One based on the anatomy, dendrite, cell body, axon, axon terminal, and the other based on the functional input region, conductor region, and output region, and that the functional description is largely dependent upon how we arrange and organize different kinds of channels in the membrane of the neuron, with the ligand-gated channels being confined to the input region, the voltage-gated channels largely being confined to the conductor region, the voltage-gated calcium channels largely being found in the axon terminal or the output region, which will now lead to the release of neurotransmitter that will then communicate to the next cell. The nervous system is largely just a daisy chain of one neuron connected to the next at these sites of input to output, or output to input, I should say. So any questions up to there? Well, if not, let me take this cell and redraw it. And this will be a little bit of a review from what we had earlier when we talked about kinesin and dynein. So I can go through it fairly quickly. But I want you to recognize that once we have this discovery of the law of dynamic polarization, in fact, let me take a break. Let me show you this couple of pictures. This is a picture I kind of like a lot. Most of this is just because I like the picture. This is actually a postcard. It was sent from Madrid. Why they had a postcard of Santiago Ramon y Cajal sitting in his laboratory, I have no idea. But this is Santiago Ramon y Cajal. Here he is in his laboratory with all these different bottles of stain in the background, and sitting around his microscope, sitting there pensively. I imagine him thinking Golgi's an idiot. But what he did is he would view the microscope in the morning, go out and take a break, and then he would come back and draw the images of the neurons. And for probably 70 years, these were the very best descriptions of neurons we had. It wasn't until the late 1960s, when people began to inject fluorescent dyes into cells, that we could begin to see the outline of neurons in their detail. Up to that point, it was all through the Golgi stain. And when he did this, these are one of these drawings that he made, and this is actually a diagram, a series of drawings taken from a pigeon cortex, cerebral cortex. And I imagine it could be one of the pigeons he'd been feeding. But what I want you to see is there are these typical regions. This is a dendrite. It is gigantic. He called them dendrite because it looked like a tree to him. So these are the input regions. And this is a cell body. And then there's an axon that comes out of the cell body. This structure here, this is what we commonly, to this day, call a pyramidal cell. For the pyramidal cell, here is the cell body. These are the dendrites. And this is the axon. And Cajal recognized that this was the input region, and the law of dynamic polarization said that information was coming into the dendrite, coming over the cell body, and then being propagated along the axon. That was the law of dynamic polarization, unidirectional flow in neurons. And he derived that simply by looking at thousands at least, of individual neurons stained with the Golgi stain, and derived that idea. We had dendrite, cell body, axon, and the information flow was from the dendrite, the cell body, to the axon. And that was all done from looking at thousands and thousands of different cells. But what he didn't know, although he started the wheels turning, was that with the structure of that neuron, with the fact that it was so highly polarized, with the fact that it had a cell body and an axon and a terminal, and knowing that some of those axons could literally be more than a meter long, he opened the idea to a logistical question. How does the neuron manage to provide protein to all of those parts of the cell? Because the neuron is a highly asymmetric cell. And that highly asymmetric structure then imposed certain requirements onto this unusual cell type. So we can take this panel and simply say that neurons are asymmetric. That asymmetry is shown in the upper figure, and I'll draw it again. And I'll remind you that in the neuronal cell body, part of the input region, we have a nucleus. And they're usually not far from the nucleus. We have free ribosomes. It became fairly apparent once we had electron microscopy that these ribosomes only rarely left the region of the cell body and the dendrites. They hardly ever were found in the axon, occasionally, but not very often. But more importantly was the idea that we had endoplasmic reticulum. And that the endoplasmic reticulum that was decorated with the ribosomes that we talked about a couple of weeks ago, this so-called rough ER, was responsible for a particular set of proteins to be synthesized, and among them were the transmembrane proteins. And also secreted proteins. Well, if you imagine a motor neuron that's in the cervical spinal cord of a giraffe, and that motor neuron then goes out into the periphery. It's part of the peripheral nervous system. It's part of the efferent system, and goes and innervates a muscle somewhere in the leg of that giraffe. That's a mighty long neuron. It may be up to a meter long, more. And yet, all the proteins that neuron's going to use have to be produced in the cell body. So this asymmetric neuron generates its own logistical supply problem. How do you manage to get the proteins from where they're produced here in the cell body to where they're going to be used, which may be all along the axon, all the way down to the axon terminal? And of course, you know the answer to that. You know that all along the axon are these structures called microtubules. And when they began to investigate the orientation of the microtubules, they always found they were oriented such that the minus ends were close to the cell body, and the plus ends were pointed away from the cell body. So that gave those microtubules an orientation. That orientation could now be exploited by using kinesin as a plus end directed motor, and similarly using dynein as a minus end directed motor. So the vesicles which are being produced by the ER and budding off of the Golgi, those vesicles now can be used as cargo carrying containers because they can get onto the microtubules and then be carried by the kinesin. Now, if we average the rate at which these molecules are moving at a rate of about These molecules are moving at a rate of about 200 to 400 millimeters per day. Which doesn't seem very fast, but remember, from the rate of the kinesin enzymatic activity, we're stepping, we're moving 200 to 400 millimeters per day in steps of 8 nanometers. So each of the feet of the kinesin is making an 8 nanometer step. So this kinesin is picking them up and putting them down pretty fast in order to get those vesicles at that rate. And we have sorted this out. We know pretty much how that happens. But it turns out that they also discovered at the same time that there was a transport rate of soluble proteins. Could read cytoplasmic. That was moving at about 0.5 to 2 millimeters per day. So, 2 orders of magnitude slower. The kinesin story was sorted out in a few years. The dynein story a few years after that. The story about the soluble or cytoplasmic proteins wasn't sorted out until a couple of years ago. And they have very different, and it was thought they had very different mechanisms. At the time that the kinesin story was being generated, it was thought the proteins were produced on the free ribosomes were generated and in some way squeezed down the axon, as though they were being squeezed down the axon like forcing the toothpaste out of a tube of toothpaste. We now know that's wrong. We now know that the fast exoplasmic transport, of course, this is generated by motor proteins. But it turns out that the slow exoplasmic transport comes by a different mechanism. Now, before I get into that, see if I have time. Yes, I have time. Let me tell you how this was sorted out, because I think these are really interesting experiments. And this is where students begin to say, why are you telling me about rabbit retinas? But there's a method to this. And what I want to tell you is how these distinctions in the rate of transport were initially sorted out. And there were a number of people who worked on this, a guy named Sidney Oakes and a guy named Black and Lassick. And they realized that if we followed the rules that protein was synthesized in the neurons, they realized that they could take the retina. And they knew that in the retina there were a series of neurons. Put them in green. And these series of neurons, called retinal ganglion cells, had their cell bodies in the retina. But they also knew that those retinal ganglion cells extended processes into the optic nerve. And from the anatomy, they knew that these neurons, I'll show this with a Y, had their output regions in a part of the brain known as the thalamus. For the anatomist among you, this is the lateral geniculate. So they knew the anatomy, they knew where the cell bodies were, they knew where the axon terminals were, and they wanted to know more about how these neurons regulated the movement of proteins that they generated in the cell body. So they did a very simple experiment. They took rabbits, and they needed rabbits because they needed a fairly long optic nerve. They needed a fairly large animal. And they did the experiment where they would inject into the vitreous humor radioactive amino acids. The radioactive amino acids would then be taken up by the cell bodies of those ganglion cells. And in the ganglion cells, those amino acids would be converted to proteins. They would both be converted to cytoplasmic proteins, and they would be converted to proteins that were packaged into vesicles. So then what they did is they took these rabbits, they injected their eyes with radioactive amino acids, and then they would wait a period of time, sometimes a few hours and sometimes more than a day. They would kill the animal, and then they would dissect out the optic nerve. So this is meant to be the optic nerve. And then they would cut sections of the optic nerve, take little pieces. And they would analyze these sections for radioactive amino acids. And by controlling the amount of time they would wait after injecting the amino acids until they killed the animal and took the sample, they could then begin to get a rate of movement of radioactive proteins in the optic nerve. And when they plotted radioactivity versus time, they found that there were two peaks of radioactivity. And the longer they waited, the farther apart the two peaks got. And from that, by waiting for a certain period of time after they'd injected the radioactive amino acids, and then looking at where and when they would find the radioactivity, and knowing that they had flow, they had unidirectional flow from the cell body toward the axon terminal, they could then from that figure out how fast these proteins were moving. And they found two components. They found a slow component and they found a fast component. They found the slow component moved at 0.5 to 2 millimeters per day. And they found that the fast component moved about 200 to 400 millimeters per day. So they said there was a fast exoplasmic transport rate and a slow exoplasmic transport rate. And then Ron Vale and others, including Tom Rees and some other people, then began to look at the kinesin. They were the ones who discovered the kinesin and the microtubules and how the microtubules provided a framework along which kinesin would move the vesicles. That then nicely translated into the transmembrane proteins, proteins being moved in vesicles being the fast component. But then they also found that there was a slow component. This one was based on kinesin and microtubules. This one they didn't know. And that wasn't sorted out until a couple of years ago. And there were some clever tricks with fluorescence microscopy which sorted out. The long and the short of it is, if we go back to this image, when they began to look at proteins in the slow component, that is cytoplasmic proteins, and look at the rate of movement and how the cytoplasmic proteins moved, they found that on average, true enough, they were moving at half a millimeter a day, about 0.5 to 2 millimeters a day. And that was the cytoplasmic proteins. But when they began to label them and watch carefully, they found that the proteins in the slow component moved intermittently. That when they moved, they were moving at the rate of 200 to 400 millimeters per day. They were moving at the fast exoplasmic transport rate, and then became apparent that this was being transported by kinesin. But what made the distinction between the vesicular movement and the cytoplasmic protein movement wasn't the rate at which they were moving, but how consistently they were moving. Vesicles were consistently moving. They got on the train and they moved right out. Whereas the proteins in the cytoplasmic component were moving and stopping, moving and stopping. And I think one of the best summaries, and I'll finish this with a story from Chelsea Green, who was a TA in the course. Oh, she's now a physician in Massachusetts. But her idea of this, and I think it really points it out, is it's like a hitchhiker. And you can imagine that if you want to hitchhike from here to Albuquerque, I don't suggest you do this, but if you want to hitchhike from here to Albuquerque, you go out to the interstate and you stick up your thumb and you wait for someone to come along and pick you up. Well, you may wait there for some period of time, but once you're getting picked up and you get in the car, then you're moving at fast rates. You're moving with the rest of traffic. The problem is the person you get a ride with only wants to go from Fort Collins to Berthoud. And so you go from Fort Collins to Berthoud, he stops, he lets you off. You put up your thumb, someone else comes along, picks you up, person picks you up, and you get in the car and you talk, you say, where are you going? And they say, oh, I'm going to Colorado Springs. And so you get in the car, and as long as you're in the car going to Colorado Springs, you're moving at a fast rate of traffic. But now you get to Colorado Springs, you have to get out of the car and find another ride. So you move in fits and starts, just like the slow component. The slow component is moving in fits and starts. It's spending a lot of time hanging around by the roadside, waiting to be cut out, put back on to a microtubule, and moved along the microtubule. Exactly how that cutting occurs isn't clear. How that piece of fabric of the cytoplasm gets attached to the microtubule isn't clear. We haven't sorted that out yet, but we do know now that these slow component proteins, the cytoplasmic proteins, are moving on average slowly, 0.5 to 2 millimeters per day. But when they're moving at fast rates. It's just they're spending a lot of time waiting to hitch another ride along the microtubules. So any questions on that? If not, I'll let you go, and we'll come back to these ideas tomorrow.